This is Module 9, Lecture Note 17. This should be the first set of lecture notes after the Christmas break. And we're going to start off by talking about polyatomic ions. Remember the prefix poly means many. And so this is many atoms that are grouped together, and they've either lost or gained some electrons, which makes them an ion. They have a charge. And there are many common polyatomic ions. And in first year chemistry, it is super important that you know the basic ones. And that is why I think it's important that you memorize them. It will be helpful when you're writing formulas. And then as we do more things this semester, just knowing them off the top of your head will make things so much easier for you. And so that is why they are required to be memorized. You do need to know the name as well as the formula, and the formula back to the name. So you need to know them both directions. On your calendar, you will be able to look up the date for your quiz. I'm not sure that it's next week, but you want to look up that date and make sure you study for it. I think the best way to study these is to do flashcards over and over and over again until you know them by heart. You can also use Quizlet. It's an online flashcard making site, and I think some students have already gone in there and put this whole list in there. So you might just go to Quizlet and look up Mrs. Nixon, and you will find some polyatomic ion quizzes that have already been created for my classes. Okay, so I'm going to go through this list and just properly pronounce each of these. This is ammonium hydroxide, chlorate, notice it has the chlorine ion, chlorite, nitrate and nitrite have the nitrogen ion, acetate, cyanide. Over here we have phosphate with phosphorus, carbonate has carbon, chromate and dichromate have chromium, and then sulfate and sulfite have sulfur. Okay. Memorizing them will take some time, but one thing that you might notice is all of the ones in this column have a 1 charge. They all have a -1 charge, except for ammonium. It is the only positive ion. Over here, these are the ones that have either a -2 or -3 charge. And phosphate is the only one that has a -3. Okay, so they're mostly 1s, a bunch of 2s, and one that has a -3 charge. The other thing I would point out is that there's often a few pairs, like chlorate and chlorite are very similar except for the number of oxygens they have. And notice the ite always has 1 less. And I remember it that the ate the ite. Okay, 8 has 1 more than ite. The only other thing I would point out is the prefix di should help you when writing this formula. Di means 2, so it's telling you 2 chromiums in dichromate. Okay, those are the tricks that I would pass on, but really focus on this because I promise it will help you. All right, in this section, we're going to learn how to write some formulas using these polyatomic ions. So if someone told you to write the formula for calcium nitrate, the first thing you need to do is look up the charge on the metal, and that's going to be calcium. And when I say look up the charge, remember you're looking at how many electrons it likes to gain or lose to be like the nearest noble gas. And calcium prefers to be a +2. And then nitrate, once you have that memorized, you'll say, oh, nitrate. NO3, 1-. It's nitrogen, oxygen, and it has a 1- charge. Okay, Now, when we're writing these formulas, I think it's important to put the polyatomic in parentheses. Because remember, when we're writing formulas, we're going to be crossing the charges. And we don't want to mess with this polyatomic. It stays grouped together as a unit. The only thing you are crossing is the 2 to the bottom and the 1 to the bottom. You're crisscrossing the charges, but you are not messing with the polyatomic ion as a unit. So you would rewrite this as CaNO3 with a 2 on the outside. That's saying you need 1 calcium and 2 nitrate groups for this formula. Let's try another one so that we're sure we have the hang of this. Barium also likes to be a +2. Carbonate is CO3 with a 2- charge. We're going to be crisscrossing and reducing if possible. And because both of these charges are 2s, they would reduce to Ba, CO3. You can still keep parentheses if you want. It really doesn't matter. But technically, because we don't need multiple of the carbonate groups, you really don't need the parentheses there. Okay, I'd like you to try magnesium phosphate on your own, and then we will check answers. Okay, so magnesium's a +2, phosphate's a -3. You're going to crisscross and end up with Mg3. It crosses to the inside, PO4, magnesium phosphate. And then in our last one, we have iron 3 acetate. And remember, iron is here in the transition metals, so it can change its charge depending on who it's bonding with. And that's why the Roman numeral is here, to help you know in this problem, iron wants to be a +3. And we're going to bond it to acetate, which is a -1. You're going to crisscross and end up with Fe. The 1 comes to the inside, so you don't have to write it. C2H3O2 with a 3 on the outside. And that's how that should look. Okay? All right, for these last 2 practice problems in this section, we're going to be writing the formulas for copper 2 hydroxide and copper 2 oxide. Now that we know how to write formulas with polyatomics and how to write formulas with regular nonmetals, it's important that you pay attention to what the question is asking. Okay, in this first problem, hydroxide is one of your polyatomics. That is very different from oxide, which is just oxygen. So as you're doing these problems that are mixed, you want to take note whether you're using a large polyatomic ion or you're just using an element off the periodic table, okay? That way you don't get them switched. So I'd like you to look at these 2 problems and see if you can correctly write the formulas for them. So in the first problem, I am crossing copper 2 with hydroxide. I switch the charges and end up with CuOH with a 2 on the outside of the parentheses. And in this one, copper 2 oxide, I'm crossing copper with oxygen. And because they're both 2 charges, when I crisscross and reduce, I just end up with CuO. So in your homework, you will get the hang of this, but double check what it's asking before you start looking up charges and crisscrossing. All right, the next thing we're going to look at in this lesson is how to draw molecular structures in 3 dimensions. So before Christmas break, we left off with learning how to draw structures for different molecules. So let's look at CH4 and do a quick review. Remember, when you want to draw a molecule, you want to first add up the number of valence electrons. So for carbon, carbon's in column 4, so it would get 4 valence. And hydrogen is in the first column, so it would get 1, but there's 4 hydrogens. Okay, so remember, you add those together, we get a total of 8, and then you always divide by 2 to tell you how many lines you're allowed in your Lewis structure or your drawing. So the way we've learned to draw this is to put carbon in the center, and you're allowed 4 lines to connect each of your hydrogens. Okay, and so that's what CH4 would look like. This is a 2D drawing, okay? It is showing that this molecule is flat on the paper. But we know in reality, molecules are not flat. They are moving around in space all around us. And in fact, they're 3-dimensional. So today we're going to learn about something called VSEPR theory. And it stands for valence shell electron pair repulsion theory. And it is the theory that lets us visualize molecules in 3 dimensions. It says that molecules will take on whatever shape keeps the valence electrons as far apart as possible. So instead of this molecule being flat in 2 dimensions, if we allowed it to be drawn in 3 dimensions, we would want these hydrogens to be as far apart as possible. Because remember, there's electrons. Remember, each hydrogen has an electron, and they are negatively charged and they repel. They want to get as far away from one another as possible. Well, in this 2-dimensional drawing, these hydrogens are 90 degrees apart from each other. But VSEPR theory says in 3 dimensions, we can get those hydrogens even further away from each other than that. So the way we would draw this in 3D is we would have 1 hydrogen to the right, 1 hydrogen going up, and then we use kind of a wedge to show a hydrogen coming out of the paper and a dotted line to show a hydrogen going into the paper. And so you can kind of see this in 3 dimensions. And instead of the hydrogens being only 90 degrees apart from each other, in 3 dimensions, these would be 109 degrees apart from each other. So you can see the difference between a 2D flat drawing of CH4 and a 3-dimensional drawing of CH4. Okay, so let's flip the paper over and look at this in a little bit more detail. Okay, on the back of your paper, you have a chart that looks like this, and mine is filled in. On the side of your chart, you have the names of the 5 different shapes of molecules that we're going to learn in this class. I would like you to pause the video at this point and take some time to carefully fill in your chart so that it looks like mine and you have all the information correct, and then come back to the video and press play, and I will go through each shape and explain it in more detail. Okay, the first 3D shape is called linear, and that should be easy to remember. Linear, think line. And a linear molecule will either have 2 total atoms, or it could have 3 total atoms. Okay, so those are the 2 possibilities. Okay, when we look at these other columns, the number of bonds on the center atom, if you just have a linear molecule like this, there isn't really a center atom. So that's why I have a 0. And for this one, these are double bonded, okay, like this example here. So it would have 2 bonds or 2 connections to the center atom. There are no unbonded pairs, and you do need to memorize the bond angle. And so you're thinking about how far apart are the atoms on the exterior from each other. And we would say that in a linear molecule, they are 180 degrees apart. Okay? Same thing for this one. 180 degrees between your two outer atoms. So that is what linear would look like. This shape is called bent. You have one atom in the center, and you have two bonds to the center atom. So you have a total of 3 atoms, 2 bonds on the center, and notice you have one unbonded pair of electrons. And that's what this represents in the picture, and what is represented by my pipe cleaner here. This is a cloud of electrons sitting on the top that is not bonded to anything, and it pushes these legs of the atom downward. So instead of being straight out like a linear, because it has this unbonded cloud, the legs of this are pushed downward into a bent position. And the bond angles for bent are 105 between the two outer atoms. That one is bent. Trigonal planar looks like this. I remember trigonal, tri, meaning 3, and planar means it should be flat. It should be all in one plane. There are 4 total atoms, 3 bonds to the center, and there are no unbonded pairs. So there are no extra electrons that are going to push the legs down. This is a completely flat molecule. It's all in one plane. And the bond angles are 120 degrees. Trigonal planar. This is trigonal pyramidal. So it still has tri for the prefix, so I remember it has 3 legs. But pyramidal should tell you that it is not flat. It is not in one plane like the previous one. It sits up like a pyramid. Okay. It has 4 total atoms. It has 3 bonds on the center, but it has 1 unbonded pair, and that is represented by this cloud of electrons on the top, and that is what pushes these legs downward. The bond angles are 107 degrees. Trigonal pyramidal. The last one we want to look at is called tetrahedral. Tetra means 4. So it should have 4 bonds on the center. Okay. There's 5 total atoms, 4 bonds on the center. There are no unbonded pairs. And the bond angles are 109 degrees. Tetrahedral. So these are all evenly spaced apart. Tetrahedral. Okay, so you will be doing a lab with constructing different molecules, and I think that is the best way to really play with them and see what their shapes become in 3 dimensions. I will also be sending the models that I used into class with you so that you can see them, touch them, and get a feel for what they look like in person. And then from this chart, really what you should be studying is the name of the molecule, and you need to know if it has unbonded pairs or not, and then the bond angle that it forms.